So today we will talk about matrices and determinants. I will do this a little bit different than it is done in the book, or actually not that much different, but in a different order. Nevertheless, I recommend that you also read the book, because it's also always good to hear things or to look at things from a different perspective. Because that can help you also in getting a better understanding of it. So if we look at the book and we look at how the book defines matrices, then the book says a matrix is an array of numeric elements that follow certain arithmetic rules. So we have an array of numeric elements. So that sounds pretty similar to what we had when we introduced the vector concept, because we introduced the vector as an ordered n-tuple of values. So we also had a set of scalar values, but they were ordered. And here we have also a set of scalar values, but they are arranged in an array. So there is also an order, but this time the order is two-dimensional. Yeah, because an array is defined by its rows and its columns. So a matrix is specified by rows and columns, m rows and n columns, which are then called the dimensions of the matrix, similar to the value n, which is the number of coefficients in a vector, which is the dimension of the vector. In relation to matrices, we often speak of coefficients then instead of coordinates in terms of a vector when we interpret it geometrically. And the notation for a matrix, we often use here uppercase values, and we use these large brackets around the sorted field of coefficients to illustrate that this is a matrix. We'll see later where we use a stroke instead of these brackets. Good. So this is just a pretty straightforward definition, and like in the case of vectors, there are also certain special cases. So for example, since we have two dimensions, they can have also relation to each other, so they can be the same, for example. So if we have the same number of columns and the same number of rows, we speak of a square matrix. And if there are certain matrices that have special characteristics, and in a lot of cases it turns out that if we have a matrix where all the values that are not in the diagonal are zero, are quite useful in certain situations, which is why they have a special name. We call these coordinates a diagonal, these matrices a diagonal matrix. And if those values in the diagonal have a value of 1, are all 1, then we call this the identity matrix. We will see later why we choose this name for it, and we denote it with IM because it's a square matrix. We only have one dimension, or we have two dimensions, but each dimension has the same value, which is why we can only denote it with one value, in this case M. But also, depending on the context, we sometimes leave it out and just write a large letter I to denote the identity matrix. And if those values in the diagonal are also zero, then we have another type of matrix which we call the zero matrix, which we denote with a large O or a large 0. So that is the matrix where all coefficients are 0. Good. So this is just a pretty straightforward definition of it. Now we said a matrix is an array of numeric elements with certain arithmetic rules. So let's look at what kind of arithmetics we can do with matrices. First thing we define is matrix addition, and like in a vector case, this is pretty straightforward because the addition is defined as just, if we have two matrices, we just add up each coefficient with the related coefficient in the other matrix. So if we have a coefficient aij in the first one, then the new coefficient cij is created by adding that coefficient with the related one from the second matrix. So for example here, it's really pretty basic. Here we have coefficient value 5, here we have 11. These are both at the same index position, so we add them up and we get 16. So we see here this addition is only defined if we have matrices with the same dimension, and also it implicitly defines the dimension of the resulting matrix, which is then again the same as the original one. So pretty straightforward. Similarly, we can define subtraction. same as with addition, only instead of a plus we have a minus here, of course, and that means if we subtract the matrices from each other, for example here again we have 5 and 11, but now 5 minus 11, so we get minus 6 here. And again, the dimensions of the original matrices have to be the same, and the resulting matrix also has the same dimension. And so this is actually pretty similar to the vector case, only now for 2 dimension instead of 1 dimension for the vector, where we just had 1 column. And similar to the vector case, where we defined multiplication with a scalar by just multiplying each coordinate of the vector with this scalar value, we define multiplication of a matrix with a scalar by just multiplying each coefficient of the matrix with the scalar. So we see here, if we use the scalar 2, here is our coordinate 5, then we get as a result a 10, and for all the others again we get the double, 2 times the value, because we multiply the same scalar value with each coefficient. And we also see here that in this case there are no restrictions on the dimensions of the matrix, because of course it's a scalar value, so we can multiply it with any kind of matrix that we have. Good. So we see here we have some very simple arithmetic, simple operations, and we defined them quite similar to the vector case, but also in the vector case then we thought about, can we also multiply vectors, and we've seen that there are no straightforward ways to do this, like with the addition and the multiplication with a scalar, but we came up with these different kind of multiplication. So for example, we introduced a scalar product and a dot product, and similarly in a matrix case we introduce a special kind of multiplication, and in the matrix case we define the multiplication of 2 matrices in this way, which looks a little more complicated than the others, but it's actually pretty simple if you exactly look at what it is. So you see here we multiply the coefficients, and then we sum it up over an index k that runs from k is 1 to na, which is the number of columns of the first matrix. So we go through the first matrix by column for a certain row I. So we have the row I here, and then we run this index a I k over the columns. So we go to each value here, and then each value is multiplied with the b coefficient from the second matrix, but now the index k is the row index of the coefficient, so we go down here, and that also already shows that in order to match here, that we have the same number of values here and the same number of values here. This only works, or matrix multiplication is only defined if the dimensions of the matrix fulfill this condition, namely that the number of columns of the first matrix is the same as the number of rows of the second matrix. And then we take the product of all these coefficients here, and then we sum them up, and then we end up with 5. And this is looks a little complicated now, but I usually like this kind of notation here, because if you write it down on paper, this is you can easily see it here. So what we do is we take the first coefficient of, so for example, if we want to have the Cij value here, if this is our row I and this is our column j, then we take the first one multiplied with each other, so minus 2 times 0, these two here, plus the product of this here, plus 1 times 1, plus the product of the next one, which is 8 times 0, plus the product of the next one, which is 4 times 1, and that gives us then our value Cij. So Cij is, or in this case 2 is 0 plus 1 plus 0 plus 4, that is 5. Is that correct? Yes. Good. So you see here that this is a pretty straightforward and easy way to do it. And also another reason why I like this kind of notation is because it nicely illustrates the condition that has to be fulfilled, namely that the rows and the columns of the first and the second matrix respectively have to match, and also it shows the dimensions of the resulting matrix, which is, if this is MA cross NA, and this is then MB cross NB, and of course these two here have to be the same values, and the resulting one is the number of rows of the original one, so the resulting matrix has MA, a dimension of MA cross, and then the rows of here, which is N, the columns of here, which is NB. I wrote it correct, but said it wrong. Good. All right, so yeah, it's a little more complicated. It looks a little more complicated, but it's pretty straightforward. And there are certain, of course, properties with these kind of arithmetics that we can do. So, for example, they are distributive over addition, which means that if we multiply a matrix with the sum of two matrices, we can alternatively multiply the matrix with each individual matrix and then do the sum. It is also associative, which means that we can, if we multiply three matrices with each other, it doesn't matter in which order we do it. If we first multiply the first two and then the third one, or if we multiply the second and the third with each other and then the first one, we can do this in different orders as long as we don't change the order of the matrices. That's important because matrix multiplication is not commutative. So that means we can, if we multiply a matrix A with a matrix B, we often do not get the same result as if we multiply a matrix B with matrix A. So I could make a proof for the first two statements. I will not do that, but I will do a similar proof in style of the proof later with another statement. So this is then you can do this as an exercise if you want to. But I will prove the second case, that matrix multiplication is not commutative. One way to see this is, of course, pretty straightforward, because as I said, multiplication is only defined if the dimensions of two matrices match. So if you want to show that this is not true, you just have to write down two matrices where the dimensions not match in one direction, but if you change them, then they do, where they match in one direction, but if you change the order, then they don't match anymore. So a straightforward example would be if you have a matrix A is a 2 cross 2 matrix, and matrix B is a 2 cross 3 matrix, then A multiplied with B will lead to a matrix that is correct because these two coefficients match, but B multiplied with A is not defined because then we would have 3 and 2 and they don't match, so the multiplication is not defined. So this is a pretty simple way to prove it, but of course the question is, of course, what happens if the dimensions match? Is then matrix multiplication always defined? So for example, what happens if we have square matrices? Then the dimensions would match no matter in which order we multiply them, but then still matrix multiplication is not commutative, and we can show that by just giving one example where they don't match. So I wrote an example down here, which is pretty simple, 1, 2, 3, and the other is 5, 6, 7, 8. 1, 2, 3, 4, the other is 5, 6, 7, 8. Now if you multiply that, again with this notation here, we take the first one, which is 5 times 1 plus 2 times 7 plus 14. That is 19 here. And if we do the same for the first coordinate here, we have again 5 times 1, so 5 plus, well, now we have 6 times 3, which is 18. And that means we get here as a first entry 23. Now we could also calculate the rest here, but we actually don't need that because we just want to show that multiplying A with B is not the same as multiplying B with A, which if the one coordinate is different, then of course the whole matrix will be different, no matter how the other values are. So we can basically stop here. So we find one example where matrix multiplication is not commutative, which means we have proven that in general we cannot say that matrix multiplication is commutative. Of course, there are situations where it is, but we wanted to prove the general case, and we have proven that by just finding one counterexample. Good. One example where it is actually commutative is the identity matrix that we introduced. You can see this very easily if you write down the general case. So if you write down, for example, here a matrix A11 till A, the number of rows 1, and then the same here. And if you multiply that with matrix multiplication, you see here that for each row, you just multiply the coordinate in that row, the coefficient in that row with it, and all the other values are 0. So what you get here is exactly the same matrix here. Which also explains why this is called the identity matrix, because it doesn't change the identity of the matrix you're multiplying it with. And also, if you write them in the other way around, you will also see that this again leads to the very same matrix, so you will always get the matrix A. And you also see here what I said earlier, that sometimes we don't write down the subscript here, because the dimension of the identity matrix is implicitly clear from the context, which in this case is the matrix multiplication. So we see here, because matrix multiplication is only defined if the size matches, we know the number of rows here, and because it's a square matrix, we also know the number of columns, and because it's a square matrix, we also know the number of rows. So we don't need to write the dimensions of the identity matrix in this case. So you see here, if you compare matrix multiplication to the normal multiplication of scalar values, then you see that the identity matrix is basically for matrix multiplication what the 1 value is for a regular multiplication of scalars. And likewise, the multiplication of the zero matrix is for matrix multiplication the same as what the 0 is for a regular multiplication of scalar values. If you multiply the 0 matrix with another matrix, you will always get 0. Or if you have another matrix and multiply it with 0, you will also always get 0, always get the 0 matrix, which is another example for a case where where it is actually commutative, but only in this very particular case. In most of the cases, it is not. Good. So in identity matrix, 0 matrix, another interesting matrix or important matrix that we often have is the so-called transposed matrix. The transposed matrix is created by just switching the coefficient. So if we have a coefficient aij, we replace it with the coefficient aji. So what we basically do is we take the values in this lower triangle below the diagonal and the ones here, and then we switch them pairwise with each other. So aij becomes aji and the other way around. Now, yeah, so this is a this is so simple, I usually wouldn't need an example for this. I wrote this example down to just illustrate also that in this case the dimensions will change or can change unless we have a square matrix. So if we have here the dimensions m cross n, or in this case 2 cross 3, then of course the transposed has a different dimension. It has just the other way around, n cross m. Good. Yeah, so like I said, transposed matrices, you will see later that there are certain situations where they are important, where we have to look at them. And also, of course, they have certain characteristics. And I wrote down here one of these characteristics, which we will actually need later when we do a proof of some other characteristic. And that is, if you multiply two matrices and then they take the transposed, you get the same result as if you do the transposed of the individual matrices and multiply them in reversed order. Yeah, this is just something you can accept it or you can prove it, and this is actually the example that I wanted to bring to make a more general proof. So in the previous case for the commutative thing, we wanted to show that it is not commutative, so it was enough to just show one example. Now in this case we want to prove the general case, which means showing one example isn't enough. We have to prove the general case. We have to prove that this statement is true for all possible values. So let's look at one of the not one of these, but let's look at the generic case. So let's look at the left side first. Let's look how this matrix AB does look like. That is the result of this matrix multiplication. So we write down the general version of the matrix A and the general version of the matrix B, and then we build the matrix product of these, and this is defined as if you take a value Cij, just any kind of value in there with a certain index ij, this is defined again as the first coefficient here with the first coefficient here, and then we walk down, we go down this row and we go down this column and multiply each coefficient, the matching coefficients with each other, and then we sum them up, and that is then our new coefficient Cij of the AB result matrix. And then for the left side we would need to take the transposed. Now if we look at the right side, we take the matrix A transposed and the matrix B transposed, and we switch the order. So here we have the A as the first and the B as the second. Here we have the B as the first and the B transpose as the first and the A transpose as the second. And then if we multiply this, we get a value which I called here dji. And you realize because I did the transposed here also, I changed the index. I wrote j first and then I as the second index. Yeah, I mean, these are just naming conventions, so you can just because we had it transposed, they are different now. And then you get this entry here, which is again just straightforward written down the definition. And now if you compare this one here with this here, you see that this is actually the same, only here we have the index dji, whereas here we have it at the position ij, but we haven't taken the transposed here, so here we just have AB, and we wanted to show that this here is the same as the transposed of this here. So if we take the transposed here, we switch, this is written on the diagonal now, so that's a bad drawing, so yeah, you get the idea. We switch ij with ji, so they are switched, which means that this is actually the same as cji now if we take the transposed, and that means we have here at the same index position the very same value. Also the dimensions match, because if we look here, the dimensions are NB cross MA, and here they are MA cross NB. But again, before we take the transpose, if we take the transpose, it turns around. So also we have the same dimensions here. So we have shown, because we have not used an example, but we have just written down the general case and picked up and proved it for a random coefficient, it means it is true for all coefficients, and that means we have proven the general case. So this is in generally true. And the reason why I'm pushing this so much is that each year we see it in the exams that there are like 5 or 10 people who want to prove a general case by just writing down an example. It is always good to write down an example to kind of understand something or make it clear with an illustrative case, but as a proof, if you want to prove a general case, you cannot prove it with an example. It's like the same if I say everyone failed this course, and to prove that I show you one exam from a guy who failed this course, and then I say, see, he failed it and this guy also failed it, so I have 2 examples, so everyone else failed as well. Of course, that's stupid, that doesn't work. The same way, if I want to prove you that everyone passed this course, I cannot just show you 2, I have to show you all the exams. Oh no, but the other way around, if I want to show you that not everyone passed this course, of course I just need to show you 1 exam where someone didn't pass the course. So this sounds really straightforward, and but I'm emphasizing it so much because we always see this mistake in the exercise, and this is so straightforward that I really want to highlight that. In general, I know that I'm very often like repeating stuff in this lecture and overemphasizing certain things. Like every time in the evaluation when I read them, there are some people saying, yeah, he always says that, and it's enough to say it just once. But the point is, I'm emphasizing this so much because I always see the mistakes from all the exams from previous years, and I rather have one or two people less fail this course than have no people complaining in the evaluations about me constantly repeating stuff. So, all right, good. So, wait, where am I? Oh, yeah, here. I switched the order. That's why I got confused here. Yeah, so we have some introduced certain special cases. The final special case of a matrix that we want to introduce is the so-called inverse matrix. And the inverse matrix is a matrix that has a characteristic. If we multiply a matrix with the inverse of her, then with the inverse of this matrix, we get the identity matrix. Of course, that is not always defined. First of all, it's only defined for square matrices, and even those do not always have an inverse. But if the inverse of a matrix exists, then if we multiply the matrix with the inverse, or if we multiply the inverse with the original matrix, we'll always get the identity matrix. And these matrices are very important later when we do vector transformation in the next lecture. And then we will also see why certain matrices do not have an inverse matrix, because if you look at it from a geometric interpretation, it is actually pretty obvious that this cannot be, that there might be matrices where you cannot create an inverse matrix. But yeah, so we'll talk about this later. We'll also talk about how to calculate it later. So for now, just take the definition, and like I said, they are very important in vector calculation, in graphics, because we can use them for vector calculation, vector transformation. Good, but before we come to that, yeah. Speaking of vectors, one of the reasons why matrices are so important in graphics is that we can use them to manipulate vectors. And the vector notation kind of smoothly integrates with the matrix multiplication if we interpret a vector as an n cross 1 matrix. So a matrix with n rows and just one column, which is how we denoted vectors in most of the cases. Wait, there is something wrong here. Yeah. Here. Yeah, so this is a special notation, the transpose of a vector. We learned that notation for matrices as the transpose of a matrix. And I also had this notation on the slide at the beginning when we introduced vectors, when I wrote down different vector notations, but I didn't talk about it because at that time it was just a notation that didn't make any sense. But now, if you look at it in relation to matrices, you see why we have this notation. So usually we write a vector like this as an n cross 1 matrix, but we can also, I often write it in this way, because if you write it down with the pen or with LaTeX, it is easier to write in a row. And that's why I'm using this here with the commas here. But you could also write it down without the commas, and then you have to make this T here, which means transposed, which, if you go back to the matrix notation, makes sense, because that is exactly this vector that we have here, only that we have now the rows and the columns switched. And if you write it that way and interpret it like that, then the matrix multiplication becomes just the scalar multiplication of a vector of two matrices. And if you interpret a single value as a matrix with just one coefficient, then you see that this really matches smoothly together. And we will later see why this is so important. Good. Another case where we see where this vector notation is used in relation to matrices is linear equation systems. A linear equation system is a system of equations. So we have a set of equations. So we have a system, means we have not just one equation, but we have a number of them. And linear means that the variables in that system are all to the power of 1. So we have here, for example, A11, A12, and so on equals B. These are, so the A, I, J, and the B, I are constant values or given values, and the x, let's call them xk, are the variables. And the goal of such linear equation system is then to find all values for the xi that fulfill all of these equations. Now, the question is, of course, why are we discussing this in a lecture about matrices? And the reason is, of course, that you can write them in matrix notation, and then you can solve them quite easily or quite nicely. And the matrix representation of this linear equation system is given like this here. You basically group all the constant values, the aij's, and you group all the constant values b on the right side, make a vector out of it or a matrix, and then you take the variables here and write them also in a vector. And then if you remember how matrix multiplication is defined, you will see that if you write that down, the multiplication, you get a vector here which is exactly the left side of the linear equation system. So notice here that I did not write, like I usually do, the arrow on top of the x and the b, because I'm interpreting them as matrices now, but these are of course vectors. Good, so we know now why we are discussing linear equation system in relation to matrices. But the question is, of course, why are we discussing this in a course about computer graphics? So what is the relation of linear equation system to computer graphics? And this is pretty straightforward, I hope pretty straightforward to see. If we look at an example here, or if you don't see it, I hope, now when you write it that way, when we bring all the b values from the right side to the left side, I hope that that looks familiar to you. Any idea? No one? Yeah, it's a plane. Each equation represents the implicit representation of a plane. Thank you, at least one. You're probably all too tired. It's early in the morning. So it's the implicit representation of three planes in 3D, and that means the solution of the linear equation system are all values x, y, z, so all points in a geometric interpretation, or points that are part of each of the planes, which means, like you said already, these are the intersection points. These are all the points that make up the intersection of all three planes in our 3D space. So by solving this linear equation system, we can calculate the intersection of three planes. Good, so how do we do this? How do we solve the linear equation system? If this linear equation system has a unique solution, we can solve it with an approach that is called Gaussian elimination, and we use so-called augmented matrices for it. It's just a different notation that makes it rather easy to implement or to solve this on paper. And the augmented matrix is basically, remember the matrix notation of the linear equation was AXB, so these are the constant values, and what we do here is basically just write down the constant values and do not write down the variables, because these are the ones that we want to find. So we have AXB is our augmented, AB is our augmented matrix, and then we solve that. So here's just an example in 3D, because of course the Gaussian elimination works for a linear equation system with larger numbers of equations, but in graphics, of course, we want to have the intersection of three planes. We're in 3D, so we have three variables representing our intersection points and three equations representing our planes. And this is then the augmented matrix for it. And now the idea of Gaussian elimination is basically that we do certain operations to the matrix that do not change the solution, but bring the matrix in a form where we can see the solution very easily. And to do that, we apply certain transformations that do not change the solution. And the first one is interchanging two rows, which of course makes sense, because if we write those down in a different order, for example, if we switch the order here, or if we switch the order of the lines, the rows in a matrix, the solution doesn't change. If it fulfills these three equations, if we write it down in that order, it also fulfills the equation if we write it down in different order. So that is straightforward. The second rule is we can multiply a row with a non-zero constant. That also makes sense, because if, for example, we multiply this here with 2, we get 2, 4, 6, 52. Oops. 52. Yeah, it's hard to read. 6, 4. Or the same here, if we multiply it here, 2, 4, 6, 52. That is the same. That doesn't change our solution because we just multiplied it with a scalar value. And so if a point x, y, z fulfills the original equation, it also fulfills this equation because we multiplied each factor of each coefficient with it the same way. So that doesn't change it, so we could do that. The last thing looks a little more not as straightforward, but it is actually, if you think about it, also pretty straightforward. If we add the multiple of one row to another row, it also doesn't change the solution. And the reason is, of course, because we have equations here. So if a solution fulfills the left part, that means it is 0. So if we add that to another row, it doesn't change the solution of that other row because we add something that is on the left side the same as on the right side. In this case, it is even 0 on the left and 0 on the right side. So we basically add 0 for the solution. So we don't change the solution. So what we can do is we can sum up, for example, or we have already here the multiple of 1. We can sum up those two, and we can then replace one of those with a row 4, 5, 7, and what is that? 67. And then we can replace one of those rows with it. And that doesn't change our solution. And then we can use that to transform the matrix in a way that makes it easier to see the solution. And that is this way here. So we have here our matrix A, X, B. And we want to transform this to a different representation, A dash X. And now, of course, also the B changes because here these operations also change the B value here, of course, which means that we have a different B here. But the X, all points that fulfill this equation here also fulfill that equation, because these operations that we do here, if we restrict ourselves to the permitted operations, do not change the solution. And so you see here, I want to bring the A matrix basically to the identity matrix, and we can do this by applying these things here. So if we do this column by column, so if we look for the first column, for example, what we want to have here, we want to have the 1 here. We already have that, so we don't have to do anything, but these two values do not match. They need to be 0. And we can do that by applying the third rule. So we apply the third rule here. We take the first one times -2 and add it to the second one. Then we get here -2 plus 2 is 0. That's exactly what we want. But of course we have to also update the other coefficients. So we have here -2 plus 1, which is -1. We have -4 plus 1, which is -3. And here the same for the last value. And then we do the same for this here. But here we just multiply it with -1 and add it to this one. Then we get here 0, and then the other values are updated accordingly. So we see here now the first column is correct. So we start working on the second one. We see here we have here -1 instead of 1. So we just apply the second rule, which is multiplication with a scalar. Of course, in this case, the scalar is -1. That leads here to a 1. So we apply the second rule here. Leads to a 1. Here just the sign changes, so instead of -3 and -19 we have 3 and 19. And then we see again here the column. This value is correct, but the column doesn't fit. So again we apply the third rule, in this case by multiplying it with -1 and then adding it. So the third rule gives us the correct value here. We see, because we already made this 1, 0, 0, applying this rule doesn't change these values anymore. So this is also correct. Then we have to work on this here, which is again applying the second rule, multiplying with wait, no, this is not. This should be 1. So we multiply this with 1.5 minus 1.5. That gives 1. These two have been correct already, so we have to work on these. So this was the second rule. And this we get again with the third rule. We bring these two to 0, and then we have it like this. So you see, just pretty straightforward application of the rules, and they don't change our result, which means that the final matrix also solves our original linear equation system. Now, if you remember what this augmented matrix relates to, you see that this is the augmented matrix represents this linear equation system. Now I wrote down the whole thing to illustrate again the relation between them, but you see here we always have 0 here. So these all fall out, so what stays left is x, y, and z, and we have directly our solution, so we can directly see our solution here from the linear equation system. Of course, what does that mean in a geometric way from the interpretation? When we calculate the intersection of 3 planes, what do we get in this case? A point, exactly. We have a vector that represents a point. So we have the point P, 3, 4, 5, which represents the intersection point of the 3 planes. So this is our solution. The question is, of course, is the solution of the intersection of 3 planes always one point, or do we always have a solution? And the answer is, of course, no, we don't. If we think about it, how 2 planes or how 3 planes can intersect in a 3D space, let's first look about how 2 planes can intersect in a 3D space. They can, of course, intersect in a line, which means we have an infinite number of solutions which are represented by a line. They can also, of course, be identical, which means we also have an infinite number of solutions, but in that case the solution is a plane. But they can also be parallel, which means we have 0 solutions because we have parallel planes. So, so that is what can happen if we intersect 2 planes. Now, if we try to intersect that with a 3rd plane, there are, of course, more options. So let's look first at this case here, 1. Where we have 2 planes that are identical, and then we intersect it with a 3rd one. Then, of course, the 3rd one can also be identical. So this is related to the first case. And then we have, of course, an infinite number of solutions. The 3rd one can be parallel. Then, of course, we have 0 solutions. There is actually another option, which I didn't draw here, which is that I hope that becomes clear, which is pretty much this case here on the right, that the second one is identical with one of them. So this is the related to the first case. And then also, of course, we have an infinite number of solutions. If we look at the second situation here, where we have 2 parallel planes, if we intersect that with a 3rd one, there are 3 options. One is, of course, that the 3rd one is also identical with one of the ones that we already have. So this is also the second case. Then we have 0 solutions. It could also be that it intersects both of them. Then this is also the second case. Then we also have 0 solution. Or if we take this as a second case and add the 3rd one here, which is also parallel, then of course we also get 0 solutions. Now, if we look at the 3rd case, then we can get all kinds of solutions. We can have the situation that the 3rd plane also intersects in the same line. Then the solution is, of course, a line, which means we have an infinite number of solutions. It could also happen that one of them is identical, so this is also the 3rd case. But it could also be that it intersects with both of them, of the other planes, in a line, but these lines are parallel to the original line, so then we have 0 solutions, or it could be that it intersects with the intersection line of the original planes, and that is again of course the case that we just calculated with the linear equation system, that we have just one solution, which we saw is the point that we calculated with the linear equation system. Now, a question is, of course, so this is the geometric interpretation of it. The question is, of course, what happens if we try to solve this arithmetically? Just give me a few more minutes, I'll be right done. Then, if we solve this arithmetically with the linear equation system, I got confused. It should be an E. With the linear equation system, then there are three different things aside from this case that we already had, where we have just a point. We could end up getting a line when we do our permitted operations. We can get a line where we have 0 equals b, but b is unequal to 0, so that doesn't work. That is not defined, so we cannot solve it, which means we have no solution, which means geometrically we have no intersection, which are all the cases that we have here at the top. But it could also happen that this b actually is 0. That means we end up having one line where we have 0 equals 0, which is always true. So we end up having two equations left with three unknown variables. So we cannot solve that, because to solve an equation with three unknown variables, we need three equations. So all we can do is write one variable depending in relation to the other one. And if you write that down, you will see that this actually looks like a line equation. Think about the slope-intercept form, where you have an x value, you put an x value in, and then you calculate the y value. So you can write one value depending on the other one, and that is then a line equation. And that is exactly the second case that we have, or not the second case, the case we have here, that we have a line equation. And also, of course, it can happen that this is for two lines, lines in the equation. So for two equations, we get 0 equals 0. That means we only have one equation left with three unknown variables, and that means we have a plane representation, which is exactly this case here. So we see, even if we cannot solve the linear equation system and calculate a solution, because this last case only exists, of course, if the planes are oriented in a way that they intersect in one point. Even if we cannot do that, we can use the linear equation system to calculate the geometric entity that results from the intersection of the three planes, which could be a line or a plane, or nothing if they don't intersect.